Chapter 2 of Introduction to Mathematical Philosophy by Bertrand Russell. This LibriVox recording is in the public domain. Definition of number. The question, what is a number, is one which has been often asked, but has only been correctly answered in our own time. The answer was given by Frege in 1884 in his Grundlagen der Arithmetik, footnote 1. The same answer is given more fully and with more development in his Grundgesetze der Arithmetik, volume 1, 1893. End of footnote 1. Although this book is quite short, not difficult, and of the very highest importance, it attracted almost no attention, and the definition of number, which it contains, remained practically unknown until it was rediscovered by the present author in 1901. In seeking a definition of number, the first thing to be clear about is what we may call the grammar of our inquiry. Many philosophers, when attempting to define number, are really setting to work to define plurality, which is quite a different thing. Number is what is characteristic of numbers, as man is what is characteristic of men. A plurality is not an instance of number, but of some particular number. A trio of men, for example, is an instance of the number 3, and the number 3 is an instance of number, but the trio is not an instance of number. This point may seem elementary and scarcely worth mentioning, yet it has proved too subtle for the philosophers, with few exceptions. A particular number is not identical with any collection of terms having that number. The number 3 is not identical with the trio consisting of Brown, Jones, and Robinson. The number 3 is something which all trios have in common, and which distinguishes them from other collections. A number is something that characterizes certain collections, namely, those that have that number. Instead of speaking of a collection, we shall as a rule speak of a class, or sometimes a set. Other words used in mathematics for the same thing are aggregate and manifold. We shall have much to say later on about classes. For the present, we shall say as little as possible. But there are some remarks that must be made immediately. A class or collection may be defined in two ways that at first sight seem quite distinct. We may enumerate its members, as when we say, the collection I mean is Brown, Jones, and Robinson, or we may mention a defining property, as when we speak of mankind or the inhabitants of London. The definition which enumerates is called a definition by extension, and the one which mentions a defining property is called a definition by intension. Of these two kinds of definition, the one by intension is logically more fundamental. This is shown by two considerations. One, that the extensional definition can always be reduced to an intensional one. Two, that the intensional one often cannot even theoretically be reduced to the extensional one. Each of these points needs a word of explanation. 1. Brown, Jones, and Robinson, all of them possess a certain property which is possessed by nothing else in the whole universe, namely, the property of being either Brown or Jones or Robinson. This property can be used to give a definition by intension of the class consisting of Brown and Jones and Robinson. Consider such a formula as x is Brown, or x is Jones, or x is Robinson. This formula will be true for just three x's, namely, Brown and Jones and Robinson. In this respect, it resembles a cubic equation with its three roots. It may be taken as assigning a property common to the members of the class consisting of these three men, and peculiar to them. A similar treatment can obviously be applied to any other class given in extension. 2. It is obvious that in practice we can often know a great deal about a class without being able to enumerate its members. No one man could actually enumerate all men, or even all the inhabitants of London, yet a great deal is known about each of these classes. This is enough to show that definition by extension is not necessary to knowledge about a class. But when we come to consider infinite classes, we find that enumeration is not even theoretically possible for beings who only live for a finite time. We cannot enumerate all the natural numbers. They are 0, 1, 2, 3, and so on. At some point, we must content ourselves with "and so on." We cannot enumerate all fractions or all irrational numbers or all of any other infinite collection. Thus, our knowledge in regard to all such collections can only be derived from a definition by intention. These remarks are relevant when we are seeking the definition of number in three different ways. In the first place, numbers themselves form an infinite collection, and cannot therefore be defined by enumeration. In the second place, the collections having a given number of terms themselves presumably form an infinite collection. It is to be presumed, for example, that there are an infinite collection of trios in the world, for if this were not the case, the total number of things in the world would be finite, which, though possible, seems unlikely. In the third place, we wish to define number in such a way that infinite numbers may be possible. Thus, we must be able to speak of the number of terms in an infinite collection, and such a collection must be defined by intention, that is, by a property common to all its members and peculiar to them. For many purposes, a class and a defining characteristic of it are practically interchangeable. The vital difference between the two consists in the fact that there is only one class having a given set of members, whereas there are always many different characteristics by which a given class may be defined. Men may be defined as featherless bipeds or as rational animals, or, more correctly, by the traits by which Swift delineates the Yahoos. It is this fact, that a defining characteristic is never unique, which makes classes useful. Otherwise, we could be content with the properties common and peculiar to their members. Footnote 1. As will be explained later, classes may be regarded as logical fictions, manufactured out of defining characteristics. But for the present, it will simplify our exposition to treat classes as if they were real. End of footnote 1. Any one of these properties can be used in place of the class whenever uniqueness is not important. Returning now to the definition of number, it is clear that number is a way of bringing together certain collections, namely, those that have a given number of terms. We can suppose all couples in one bundle, all trios in another, and so on. In this way, we obtain various bundles of collections, each bundle consisting of all the collections that have a certain number of terms. Each bundle is a class whose members are collections, that is, classes. Thus, each is a class of classes. The bundle consisting of all couples, for example, is a class of classes. Each couple is a class with two members, and the whole bundle of couples is a class with an infinite number of members, each of which is a class of two members. How shall we decide whether two collections are to belong to the same bundle? The answer that suggests itself is: find out how many members each has, and put them in the same bundle if they have the same number of members. But this presupposes that we have defined numbers, and that we know how to discover how many terms a collection has. We are so used to the operation of counting that such a presupposition might easily pass unnoticed. In fact, however, counting, though familiar, is logically a very complex operation. Moreover, it is only available as a means of discovering how many terms a collection has when the collection is finite. Our definition of number must not assume in advance that all numbers are finite, and we cannot, in any case, without a vicious circle, use counting to define numbers, because numbers are used in counting. We need, therefore, some other method of deciding when two collections have the same number of terms. In actual fact, it is simpler logically to find out whether two collections have the same number of terms than it is to define what that number is. An illustration will make this clear. If there were no polygamy or polyandry anywhere in the world, it is clear that the number of husbands living at any moment would be exactly the same as the number of wives. We do not need a census to assure us of this, nor do we need to know what is the actual number of husbands and wives. We know that the number must be the same in both collections, because each husband has one wife and each wife has one husband. The relation of husband and wife is what is called 1-1. A relation is said to be 1-1 when, if x has the relation in question to y, no other term x' has the same relation to y, and x does not have the same relation to any term y' other than y. When only the first of these two conditions is fulfilled, the relation is called 1-many. When only the second is fulfilled, it is called many-one. It should be observed that the number 1 is not used in these definitions. In Christian countries, the relation of husband to wife is 1-1. In Mohammedan countries, it is 1-many. In Tibet, it is many-one. The relation of father to son is 1-many. That of son to father is many-one. But that of eldest son to father is 1-1. If n is any number, the relation of n to n+1 is 1-1. So is the relation of n to 2n or to 3n. When we are considering only positive numbers, the relation of n to n² is 1-1. But when negative numbers are admitted, it becomes 2-1, since n and -n have the same square. These instances should suffice to make clear the notions of 1-1, 1-many, and many-one relations, which play a great part in the principles of mathematics, not only in relation to the definition of numbers, but in many other connections. Two classes are said to be similar when there is a 1-1 relation which correlates the terms of the one class each with one term of the other classes, in the same manner in which the relation of marriage correlates husbands with wives. A few preliminary definitions will help us to state this definition more precisely. The class of those terms that have a given relation to something or other is called the domain of that relation. Thus, fathers are the domain of the relation of father to child, husbands are the domain of the relation of husband to wife, wives are the domain of the relation of wife to husband, and husbands and wives together are the domain of the relation of marriage. The relation of wife to husband is called the converse of the relation of husband to wife. Similarly, less is the converse of greater, later is the converse of earlier, and so on. Generally, the converse of a given relation is that relation which holds between y and x whenever the given relation holds between x and y. The converse domain of a relation is the domain of its converse. Thus, the class of wives is the converse domain of the relation of husband to wife. We may now state our definition of similarity as follows. One class is said to be similar to another when there is a 1-1 relation of which the one class is the domain, while the other is the converse domain. It is easy to prove, 1, that every class is similar to itself, 2, that if a class α is similar to a class β, then β is similar to α, 3, that if α is similar to β and β to γ, then α is similar to γ. A relation is said to be reflexive when it possesses the first of these properties, symmetrical when it possesses the second, and transitive when it possesses the third. It is obvious that a relation which is symmetrical and transitive must be reflexive throughout its domain. Relations which possess these properties are an important kind, and it is worth while to note that similarity is one of this kind of relations. It is obvious to common sense that two finite classes have the same number of terms if they are similar, but not otherwise. The act of counting consists in establishing a 1-1 correlation between the set of objects counted and the natural numbers, excluding 0, that are used up in the process. Accordingly, common sense concludes that there are as many objects in the set to be counted as there are numbers up to the last number used in the counting. And we also know that, so long as we confine ourselves to finite numbers, there are just n numbers from 1 up to n. Hence it follows that the last number used in counting a collection is the number of terms in the collection, provided the collection is finite. But this result, besides being only applicable to finite collections, depends upon and assumes the fact that two classes which are similar have the same number of terms. For what we do when we count, say, 10 objects is to show that the set of these objects is similar to the set of numbers from 1 to 10. The notion of similarity is logically presupposed in the operation of counting, and is logically simpler, though less familiar. In counting, it is necessary to take the objects counted in a certain order, as first, second, third, and the rest. But order is not of the essence of number. It is an irrelevant addition, an unnecessary complication from the logical point of view. The notion of similarity does not demand an order. For example, we saw that the number of husbands is the same as the number of wives, without having to establish an order of precedence among them. The notion of similarity also does not require that the classes which are similar should be finite. Take, for example, the natural numbers excluding 0 on the one hand, and the fractions which have 1 for their numerator on the other hand. It is obvious that we can correlate 2 with 1/2, 3 with 1/3, and so on, thus proving that the two classes are similar. We may thus use the notion of similarity to decide when two collections are to belong to the same bundle, in the sense in which we were asking this question earlier in this chapter. We want to make one bundle containing the class that has no members. This will be for the number 0. Then we want a bundle of all the classes that have one member. This will be for the number 1. Then for the number 2, we want a bundle consisting of all couples, then one of all trios, and so on. Given any collection, we can define the bundle it is to belong to as being the class of all those collections that are similar to it. It is very easy to see that if, for example, a collection has 3 members, the class of all those collections that are similar to it will be the class of trios. And whatever number of terms a collection may have, those collections that are similar to it will have the same number of terms. We may take this as a definition of having the same number of terms. It is obvious that it gives results conformable to usage so long as we confine ourselves to finite collections. So far, we have not suggested anything in the slightest degree paradoxical. But when we come to the actual definition of numbers, we cannot avoid what must at first sight seem a paradox, though this impression will soon wear off. We naturally think that the class of couples, for example, is something different from the number 2. But there is no doubt about the class of couples. It is indubitable and not difficult to define, whereas the number 2, in any other sense, is a metaphysical entity about which we can never feel sure that it exists or that we have tracked it down. It is therefore more prudent to content ourselves with the class of couples which we are sure of, than to hunt for a problematical number 2 which must always remain elusive. Accordingly, we set up the following definition. The number of a class is the class of all those classes that are similar to it. Thus, the number of a couple will be the class of all couples. In fact, the class of all couples will be the number 2, according to our definition. At the expense of a little oddity, this definition secures definiteness and indubitableness, and it is not difficult to prove that numbers so defined have all the properties that we expect numbers to have. We may now go on to define numbers in general as any one of the bundles into which similarity collects classes. A number will be a set of classes such as that any two are similar to each other, and none outside the set are similar to any inside the set. In other words, a number, in general, is any collection which is the number of one of its members, or, more simply still, a number is anything which is the number of some class. Such a definition has a verbal appearance of being circular, but in fact it is not. We define the number of a given class without using the notion of number in general. Therefore, we may define number in general in terms of the number of a given class, without committing any logical error. Definitions of this sort are in fact very common. The class of fathers, for example, would have to be defined by first defining what it is to be the father of somebody. Then the class of fathers will be those who are somebody's father. Similarly, if we want to define square numbers, say, we must first define what we mean by saying that one number is the square of another, and then define square numbers as those that are the squares of other numbers. This kind of procedure is very common, and it is important to realize that it is legitimate and even often necessary. We have now given a definition of numbers which will serve for finite collections. It remains to be seen how it will serve for infinite collections. But first we must decide what we mean by finite and infinite, which cannot be done within the limits of the present chapter. End of chapter 2.